everyone is tired and there's also a badminton tournament, I think, at 6. So I'm going to try and keep this last lecture a little short. But I'll just try and explain some points which I think are important and will hopefully bring you up to date with some of the literature. So, so far, in what we have done is still kind of on the board. Okay, so everything we've said so far in bullet points is on the board. We've looked at the geometry of black hole radiation, of black holes, the derivation of Hawking radiation, this naive information paradox, how it's resolved by recognizing that pure and mixed states are very close to each other in terms of observations. Then we pointed out there's a refinement of the information paradox, which is in terms of this principle of ignorance that Hawking stated. And now what we said is, well, look, in fact, in the theory of quantum gravity, only in a theory of quantum gravity, we don't have a principle of ignorance, but rather we have a principle of holography of information, which we made precise in terms of these algebras and Scri plus. Okay. Are there any questions about this? About what we proved? Yeah.
Also, expression that was analytic.
Have you showed what?
You showed it expression that was analytic. What was the domain balance?
Domain of analyticity was the upper half plane in U. We looked at some correlation function here that was improving this result. Okay. So the domain of analyticity of that correlator was the upper half plane of U. If you look in your notes, you'll see it. So it was upper half plane. Okay. So let me just remind you how this last result that we proved. Yeah, we said that look at any operator in this Hilbert space. We expanded on a complete basis of states. By quantum mechanics, such an expansion always exists. Then we used the result on that board, which said that this state n could be written as the operator of xn on the vacuum, where xn was some operator in the small algebra. That result is proved there. This state m could be written as xm on the vacuum, but we get xm dagger because it's the bra n, not the ket m. Okay. So this comes from that result on that board. Then this operator in the middle, which is ket 0 bra 0, is the projector on the vacuum. That's always true. What is special in a theory of gravity is that this projector on the vacuum is an element of the small algebra. That is what is special in gravity. This result is also true in quantum field theory. It's, as I said, the result that we proved, they only required positivity of energy. This required us to assume that, you had the Gauss law and therefore an operator, observer at infinity could measure, the energy. And therefore, then we found that any operator in the theory could be approximated arbitrarily well by sum of products of 3 operators in the small algebra. And therefore, we argued that any operator in the theory, which could be an operator from the large algebra, could be approximated arbitrarily well from the small algebra. Okay. So I want you to be clear about where we use gravity here. Yeah.
This from FBW that all over the infinite distance, we have the same vacuum because the result is
What do you mean by same vacuum?
the 0, 0, 0.
This is the full vacuum of the theory. This is a unique state in the theory. Subject to infrared issues, which I'm not discussing right now, but this is a unique state in the theory. So there's no same. There's vacuum is not different at infinity and at the bulk. The vacuum is the state which specifies the full state of the theory everywhere in space time and has 0 energy. So there's no it's not like you have the vacuum at infinity and not the vacuum somewhere else. This vacuum is the full vacuum. It's the state of 0 energy. That's how we define this vacuum. Or the state of 0 energy, state of lowest energy. Okay, good. So now the application of this to the information paradox should be kind of clear. It is the statement that if you think of a black hole, then we assume that all black holes evaporate. So unlike people in general relativity who will be careful that a black hole Penrose diagram is different from the Minkowski space Penrose diagram, once you take into account quantum effects, the way we think of the formation and evaporation of a black hole is that something complicated happens here, then things evaporate. But in the end, asymptotically, space-time is still flat in the far future, very far away and so on. So we still think, remember when I drew this diagram, I said all we were assuming was we were in asymptotically flat space. And that's why the result we proved was really a result for asymptotically flat space. And however, what we showed is that an observer making observations near infinity, that was sufficient for this observer to determine the entire state on Scri plus. Okay. Now, there are some subtleties you should keep track of in this result. I'm not going to go into great detail with these subtleties. First, even though I was ignoring the omega coordinate here, it was important that this observer actually had to make observations on all of omega. So we are really thinking of a team of observers who make observations at different points on omega and then combine their observations. Okay, these are like observers in the celestial sphere who are very far, but they're kind of spread out. If you want to think of this room, they're kind of spread out everywhere, right, on the walls of this room. Okay. The second point is that this kind of result we prove would not work if I said you can only make observations on this side, but not observations on this side. If I restricted this omega coordinate, then in fact you would find that those observations on this side are not sufficient to get observations on this side. So observations for one hemisphere are not sufficient to get observations in the other hemisphere. So remember carefully what the geometry of this is. The statement is that observations in the complement of a compact region are sufficient to determine observations in the region. So it's not that observations in any one region are sufficient to determine observations in any other region. Okay. The other subtlety is that in this discussion, we've been a little blasé about the fact that in flat space, in fact, there are additional points on the Penrose diagram, which involve also what are called I plus and I minus, which are future time-like infinity and past time-like infinity. These points are important because they are the points where you describe where massive particles end up. Okay? So massive particles start from I minus and end up at I plus. And our discussion here has kind of ignored the fact that you have also elements of the algebra that live on I plus and I minus. I'm not going to have much to say about how to deal with this. In fact, this problem is not completely understood. But I just want to point out that if you take a black hole that's very big, then such a black hole, by the formulas we discussed in the lecture 1 or lecture 2, has very low temperature. So you can make the black hole big enough that its temperature is much smaller than the temperature of the lightest massive particle. And by doing that, you can ensure that the black hole radiates almost entirely into massless particles, which are gravitons and photons and other massless fields, and not into massive particles. Therefore, it might be reasonable to ignore the effect of massive particles in this discussion and to assume that the final state that's produced by the evaporation of such a black hole does not have much information in massive particles. Okay? So I'm going to assume from now on that we can only discuss operations on Scri plus, which, as I said, is subject to this subtlety that I just mentioned about massive particles. Okay. I said the reason we're ignoring them is, first of all, because in our treatment it's hard to treat them. But the reason we are arguing it is justified to ignore them is because you can take a black hole of large enough mass, and if you take a black hole of large enough mass, remember that the temperature goes as inversely proportional to the mass. So if you take the black hole to be a large enough mass, you can make the temperature of the black hole much lower than the mass of the lightest particle in the theory. If you do that, then that black hole doesn't radiate much into massive particles at all. So the final state that's produced by the evaporation of the black hole doesn't have too many massive particles. So therefore, you can basically just ignore the effect or the information content in those massive particles and deal with the massless particles which were emitted by the evaporation of the black hole. Yeah.
So basically, what we're saying is that there is a regime where we can solve the massive particle problem theory.
Yeah. So you can ignore the massive particles in the problem still regime. This actually is something that's common to many discussions of the information paradox, including discussions of the so-called page curves that I'll review later in this lecture, that we often ignore the effect of massive particles. It doesn't mean that massive particles are not important. Some of us, for instance, have spent some time trying to understand how to incorporate massive particles in the story. But right now, we don't have a complete story to tell about massive particles. And perhaps for questions of black hole evaporation, it's okay to ignore them. Or it seems reasonable to argue that for questions of black hole evaporation, it's okay to ignore. I'm being a little tentative here because, the arguments I'm giving are plausible, but they're not clearly watertight. So I'm going to just ignore the effect of massive particles and think of the algebra. The result I proved is still correct. All elements of the algebra Scri plus can be approximated in this algebra. The point is that the algebra of the full theory might have more elements than the algebra of Scri plus. It might also have additional elements that you need to add some I plus. And I'm not saying anything about those. Right? And that result is not false. That result is true. But there might be more operators in the full theory that are not captured in this algebra on Scri plus. Okay. Now, what is the implication of this for the information paradox? Well, the implication of this for the information paradox is kind of clear. Remember, when we discussed the refinement of the information paradox, the refinement of Hawking was that the observer outside or the field outside or degrees of freedom outside are independent of everything inside the black hole except for the total mass, charge, and angular momentum. That is the result that is classically true. But we have now shown that quantum mechanically it's manifestly false. I've shown in many examples in perturbation theory, but of course in black holes you shouldn't use perturbation theory. What we're showing is that in a full theory of quantum gravity, it is not true that the region outside the black hole or the metric or the full observables outside the black hole are independent of the infalling matter except for the mass, charge, and angular momentum. Okay. And I want to emphasize that if you think of the black hole as forming here, let me try and see if I can draw a diagram properly. Then okay, sometimes the Penrose diagram of an evaporating black hole is drawn this way. Okay. This is the same Penrose diagram as I drew earlier. This is still scribe plus. This kind of indicates that there was a singularity and then the black hole evaporated away. Okay. Neither this Penrose diagram is not a very precise diagram. It's just a way of showing that a black hole formed and then it evaporated away. Okay. So the statement that Hawking made was that look, you had some matter that fell in from here. And the statement Hawking wanted to make was that observations here on this slice were completely independent of what went in here. So the principle of ignorance said to get the state on this slice, let's call this state R, let's call this part of the slice R bar and this part R, you should trace over what's inside. Okay. However, you see that that's not correct in a theory of quantum gravity if you keep track of all degrees of freedom. If you keep track of all degrees of freedom, then in fact observations here are not only not ignorant of what's inside and not only up to the total value of mass, charge, and angular momentum, not only up to 3 numbers, but in fact all observations here are completely determine what's happening here. Okay. Therefore, this argument that was used to establish the refinement of the information paradox is not valid. The argument that Hawking used to refine the information paradox was that the Hilbert space, I wrote this at the beginning, was that the Hilbert space factorizes into HR times HR bar. I might have used other notation in the first lecture. I probably used H in times H out or something like that, or H hidden times H out. But here, let's just use HR times HR bar. So what Hawking assumed was that the Hilbert space factorizes, and to get the state on HR bar, you should trace over HR. But it's clear that, the Hilbert space doesn't factorize. If the Hilbert space were to factorize, the algebra of operators would also factorize into an algebra associated with this region and algebra associated with this region. But this region includes the part near infinity. And what we just proved is that the algebra of operators in this region, in fact, includes all of scribe plus. So this factorization is wrong. Okay. This is a wrong assumption. So if you go back to your notes, you will see this assumption being made. And this was crucial to prove the information paradox. And this assumption is wrong. Okay? And this assumption, Hawking is not the only one to have made this assumption. This assumption has been made many times in the literature subsequently. It is still made often tacitly, even though we now, I think, understand pretty well that it's wrong. If you look at the arguments that went into the firewall, which actually were earlier proposed by Samir Mathur, those were actually important arguments, they were insightful arguments, but the incorrect assumption that was made in those arguments was actually this, was to assume that the Hilbert space factorizes into a part inside and a part outside. And it is not true that in the theory of gravity, the Hilbert space can be factorized into a Hilbert space of a bounded region and the Hilbert space of the complement of a bounded region. Okay? I emphasize that this only works because R is a bounded region. Okay, so let me state some caveats, let me write them down. H is not equal to HR times HR bar when R is a bounded region. At other times it might be. So R bar always means the complement of R. Okay. And R bar is its complement. Yeah, so R was the region inside the horizon on the Cauchy slice and R bar was the region outside. Okay, so H is not given by this form. Okay. it might be given by this form if R itself extends to infinity. If I take the region to the left of this line and the region to the right of this line, then you might have a chance of writing the Hilbert space in this way. Okay. But not when R is bounded and R bar is its complement. Okay. Therefore, this tells us that this assumption that was made in deriving the information paradox is wrong, and it tells us what was the error in Hawking's argument for information loss. Okay. Let me also say something else, which is that, what Hawking was saying was correct in the classical theory, of course. In the classical theory, it looks like the degrees of freedom factorize into degrees of freedom inside and outside. But it's also correct in the quantum theory if we coarse grain our observations. Okay. So this is the second caveat I want to make. Okay. If we coarse grain observations, we might be able to effectively factorize the Hilbert space. Might factorize effectively. This is actually a very subtle point which, I don't have time to discuss in sufficient detail. But I just want to mention that, someone might say the following. And if you think about this when you go home, you might think about the following question. I have been saying that in quantum field theory, the Hilbert space factorizes, but in quantum gravity, the Hilbert space doesn't factorize. By factorization, I mean that the degrees of freedom of the whole theory cannot be divided into degrees of freedom that belong to a bounded region and a separate commutant that belongs to its complement. Okay? I've been saying in gravity that doesn't work, but in quantum field theory, I've been saying it does work. Now, you might go home and think about the following question. You might say, in our world, we do have gravity, right? And gravity really exists. But yet we use quantum field theory and we use this factorization. So how does it happen? Okay. And the answer is, if you coarse grain observations, in fact, if you don't keep track of corrections that are exponentially suppressed in the entropy, in this case, the entropy of the black hole, then it is still possible to think of an effectively factorized Hilbert space. So locality does work in, even in the presence of gravity, if you coarse grain observations a little bit. Okay? And one example, one way in which you should think about this is that you can think about this in the language of unitarity. Okay? In the language of, when we think of unitarity is a precise statement. So let's just think of unitarity in ordinary quantum field theories. Unitarity is a precise statement in ordinary quantum field theories. It's very important. It's important for us, to make sure that our theories make sense. If our theories were not unitary, we would be in big trouble. Unitarity is also something that you can verify perturbatively when you look at light excitations about the vacuum. When you do basic quantum field theory, all of you are taught to verify unitarity for the S matrix. You compute 2 to 2 scattering and check unitarity for the S matrix. On the other hand, in the real world, it often looks like physics is not unitary. Look, now this black pen stopped. Unitarity tells you that I should be able to compute from this final state what the initial state was. Okay, what happened? What happened? Is unitarity not working? Exactly. You could not keep track of all degrees of freedom. So two things happened. First, you didn't keep track of all degrees of freedom. But second, there was a background. If there was no background, if you're in the vacuum, then there was no, you'd be very easy to keep track of degrees of freedom. So there were background degrees of freedom. In this case, there was a pen, but there was a background, which was a table. Okay. And so in the presence of a background, and when you coarse grain, it looks like unitarity is lost. Okay. In the presence of a sufficiently heavy background, if you coarse grain, it looks like, the Hilbert space might factorize. So that's this point 2 here. If you coarse grain, you don't keep, coarse grain means this, what you said, if you don't keep track of all degrees of freedom, then the Hilbert space might factorize. However, if you want to ask precise questions about information loss, then you are not allowed to coarse grain. You cannot say, oh, I coarse grained, I didn't keep track of all degrees of freedom, and then I lost information. Well, obviously, right? You're not allowed to say that. So you can either decide that you want to be in a regime where locality holds precisely, and then you coarse grain, and you don't keep track of all gravitational degrees of freedom, and then things look like our mundane experience. Okay, our mundane experience, by the way, is also that physics is not unitary. Our mundane experience is physics is dissipative, actually, not that physics is unitary. Or you can decide to ask very precise questions. And if you ask very precise questions, then it's not true that the Hilbert space factorizes. Okay? And this conflation of these two regimes has been a recipe for paradoxes now for many years. And will probably continue to be a recipe for paradoxes, which is people say, look, in our mundane experience, things factorize, right? We have the coarse grain, we have locality. Therefore, we'll assume locality is exact and go ahead and derive some consequence. And if you derive a consequence, you will often run into problems, as has happened many times in the literature. Okay. And including in this refinement of the information paradox. So, the bottom line to keep in mind, I'll just come to that, is that in quantum gravity, degrees of freedom are localized very differently from our mundane experience. This is very, if you think about this more and more, you'll find it more and more confusing that in a theory of gravity, I'm saying the degrees of freedom in a region can be specified by degrees of freedom outside the region. It's a very surprising statement, very counterintuitive. But of course, that's not in contrast with the everyday experience, which is, we are local observers. We are not described by some holographic degrees of freedom. And that's because we don't keep track of all quantum gravity degrees of freedom to arbitrary precision. So you can recover a mundane experience by coarse training, just like you can recover a mundane experience of dissipation by coarse training. But you shouldn't push it too far. And the error in Hawking's argument was to push our mundane experience, which you get from here by coarse training, to derive a paradox. Okay. Are there any questions about this? Because now I'm going to close this part of this refinement of the Hawking's paradox and go on to discuss a different issue about the page curve. Yeah.
Police and other restrictivity MUA in perception of mortality critically event. A fun petos. So you think your analysis is
No, that's fine. No. That's what I said. You see, when you write down an effective Lagrangian, of course you should write down a local Lagrangian. When
to us, if we need to make more like if we think that the standard model and other things we have guarantee it's okay.
yes,
What do you say?
yes,
Maybe there has to be some sort of
but they are effective field theories. We don't think of the standard model as being a full theory of quantum gravity. If it was a full theory of quantum gravity, it would not have that form. So we don't know what the full theory of quantum gravity that describes our world is. But we know that effectively there is a light cone structure, there is locality. The standard model Lagrangian is an effective Lagrangian. It's perfectly accurate. It's in that regime. It's a coarse grained Lagrangian. You might say it's not coarse grained, but it is coarse grained because we have not kept track of all quantum gravity degrees of freedom. Now you can do more. You can actually keep track of quantum gravity degrees of freedom perturbatively in the Newton's constant. You can add the Einstein Lagrangian. You can also keep track of loop corrections due to gravity. But you have to make sure that, if you start asking very precise questions, then you will have to realize this feature. Okay? This feature is telling you that the Hilbert space doesn't factorize, and that feature is a feature of the theory, which we derived by making some assumptions about what the full UV complete theory should be, without knowing what the full UV complete theory is. Okay? Yeah.
so the extra any changes in the external region messaging it was a complicated literally
Actually, that's not correct. More that any changes in R will lead to changes in R bar. You might be able to make changes in R bar that are not reflected in R. Okay. Okay. So is this point clear? What the proposal is that there was this refinement of the information paradox, and that refinement of the information paradox relies on factorization. And anytime you see a paradox in the literature which talks about black holes, starts assuming factorization, but then starts making precise statements based on that, like fundamental statements, that's a recipe for a paradox. Okay? That doesn't mean you can never think of factorization. Of course you can. We do it all the time in a real. And the way you should do it is you should coarse grain. Okay? And in fact, there's a lot of recent literature on this coarse grained physics, which is literature for Neumann algebras, which talks about algebras of subregions of gravity, and that's really in this regime. Okay? So there's recent work on the so-called type 2 von Neumann algebras, which is in that regime. Okay, that what I said right now is not a statement you necessarily need to understand fully, but you might hear these words about type 2 von Neumann algebras, and that's in simpler language this regime, where you've coarse trained. Is what? Yeah, you do have phonemics. So these type 2 algebras are coarse-grained algebras. Well, it'll take us too far afield to define these, but you can define coarse-grained algebras for subregions, and these, including some gravitational effects, and these are what are called type 2 algebras. If you don't constrain, you would not get these type 2 algebras. You would find that, a different kind of algebra. It's called a type 1 algebra. But yeah, let's, I don't want to go too much into that discussion. We can have that discussion separately. It'll take us too far afield from the information paradox. Okay. Okay, good. So now I want to shift gears and spend the last part discussing a different topic, which is the topic of the page curve. In fact, we're going to go back to factorized Hilbert spaces, even though I just said that was wrong. But the page curve is all about factorized Hilbert spaces. Okay. Okay. So I now want to discuss the page curve. Now, in fact, the page curve is an interesting analysis. It's yet another one of those analyses that you should know about, even if you don't study black holes. Okay, so the page curve turns out to be important in condensed matter systems. The page curve is just something that's a relevant result in quantum information, even though it was first derived by thinking about black holes. Okay, so it's yet, as I said, sometimes by thinking about black holes, we learn various lessons. Sometimes those lessons don't even have to do with gravity. And I think, in fact, the page curve is an interesting result. It's not that interesting in gravity, but it's more interesting in non-gravitational systems. Okay, I'll explain what the result is. So, okay, so I'm shifting gears now. Are there any other questions about this part of what I said, or can I shift gears to the page curve? Yeah. Yeah, yes. This? Well, it's part of 6. It's the way we made 6 precise. 6, this was just a cartoon, right? I said degrees of freedom here are here. This is just a cartoon. This is the precise statement of this. When we say observations here have another representation here, what we really mean, the way we make it precise, is all elements of A of scribe plus can be approximated arbitrarily well in A minus infinity. Why is this making it precise? Because A minus infinity is like the algebra near the boundary of scribe plus. So you can think of A minus infinity as being this algebra. It's the algebra outside some region. And the algebra of A of scribe plus is the full algebra. So it's a statement that all operators have a representation near the boundary, which is like a realization of this cartoon. But the reason it's made on scribe plus is because we can never make this cartoon, at least right now, we don't know how to make this cartoon precise in the bulk, even though it's a cartoon. We only make it precise in asymptotic infinity, which makes sense. This only makes sense in the gravitational context, absolutely. Otherwise, it's not true. Okay, so let me now go on and talk about the page curve. So I'm shifting gears right now. If some of you were a little lost, please wake up, because I'm going to say something which is different. It's just some result that you should all know, and it's about factorized Hilbert spaces. Even though I said this assumption is wrong, I'll keep this on the board. But we'll come back to that. Let me erase this and let me keep this part on the board. Oh no. Okay. Okay, good. Okay, so let's talk about the page curve. So let's consider a case where you do have a factorized Hilbert space. Okay, forget about what I said about gravity. Just think of a system of qubits where you're making measurements on one qubit or another qubit, and gravity is very weak. It's kind of irrelevant, okay, for what we're discussing. So as I said, it's not true. We never have effective factorization. If I have a quantum computer in my lab, I do have effective factorization in degrees of freedom of the different qubits. So imagine we have a Hilbert space, which can be written as a Hilbert space of m dimensions cross a Hilbert space of n dimensions. Okay, so dim of Hm is m, and dim of Hn is n. Okay, and let's assume, without loss of generality, m is smaller than n. Okay, there's no loss of generality because I just call whatever is smaller m and whatever is bigger n. Okay, is this clear? We just have a Hilbert. This can be a Hilbert space of maybe 10 qubits and 20 qubits. Maybe you have 10 qubits and this is 20 qubits. If you have 10 qubits, what is m? If this describes a Hilbert space of 10 qubits, what is m? 2 to the 10, right? So m is 2 to the 10. If this describes a Hilbert space of n qubits, of 20 qubits, then n is 2 to the 20. Okay. So remember, m and n are not the number of qubits. M and n are the dimensions of the Hilbert spaces. They might be exponential in some physical measure like the number of qubits. Okay. Excellent. So take a generic state. Consider a generic state. How do you pick a generic state? Well, you have to pick it using the Haar measure. Remember the discussion we had about how you pick generic states by integrating over all states using the Haar measure? It's the same discussion. I'm not going to go through all the details, but generic here means the same thing. Such a state can be written as let me write it properly. One to n, sum of i's will to 1 to n. Do you agree with this statement that for some coefficients aij, not this is m. Yeah. Is this, obviously you can write such as any state in the full theory this way, right? As a combination of a state from hm and a state from hm. This I runs over 1 to m, it's a basis for this Hilbert space. And this j runs over 1 to n, it's a basis for this Hilbert space. You see this? Okay, good. Now, there's a standard result in quantum mechanics that tells you by change of basis, we can write A in the following form. Okay, this sometimes called a singular value decomposition. A is actually a rectangular matrix. You can't strictly diagonalize it, but you can write it in the following form, where you have some coefficients here, and all other entries are 0. Everything else is 0. Okay. This is a standard result in linear algebra. If you give a rectangular matrix, you can convert it to this form. So this side is n. This dimension is n of this matrix. This dimension is m. And I can arrange it so that it has diagonal elements from here to here. These are not really diagonal. And it has zeros everywhere else. Okay. And this is called a singular value decomposition, but you can always do this. Okay. If you do this, then the elements of the density matrix that you get for the Hilbert space, the eigenvalues of the density matrix are mod of A11 squared, mod of A22 squared, and so on up to mod of AMM squared. So in a special basis, okay. So here I wrote the state, a generic state has to be written as Aij in this basis, okay, in a general basis. This Aij doesn't have any specific structure. By means of this change of basis, I can convert this matrix to being that form, okay, so that the sum only goes over 1 to m and only over diagonal terms. And in this basis, the eigenvalues of rho m are given by this. Maybe to avoid confusion, well, okay. What I wrote here is a little confusing, so please make a note in your notes. I wrote A as a matrix which was a rectangular matrix, a general rectangular matrix, and then I did a basis change here. So the A's that appear in the second line are not the same as the A's that appear in the first line. Okay, please be a little careful about this notation. I then went to this basis and I went here. So this board should have interposed between these two lines. Okay, but okay, I can put a tilde on it if you like, but okay, let's put a tilde. Okay. Okay, I've put a tilde on it to indicate this. Fine. Okay, good. What is now the the entropy of this Hilbert's of the left Hilbert space? Okay, the entropy is given by Sm is equal to minus trace of rho m log rho n. Okay, and what is that given by? Well, it's given by sum over I a tilde I squared log of a tilde I squared. You agree? Log of a tilde minus of this. Okay. So the density matrix turns out to have these eigenvalues. You can easily check just by taking, the way to check this formula is you go to the special basis, there the states will become diagonal. Okay. And then you just trace out the other side. So you can check this. Okay. If you just know how to get a density matrix by doing a partial trace, you can check what I've written here. Okay. Then the entropy is given by rho m log rho m. So it's given by sum of ai square log of ai square. You agree with this? This entropy, of course, depends on what the specific eigenvalues a tilde ai are, right? However, what do we expect it to be for a generic state if you take most states in the Hilbert space? Any guesses? What do you expect the value of this ai tilde squared to be for a generic state? Huh? Well, it's non-zero for sure. Yeah, that's true. Positive also is true because it's mod square of a complex number, so it has to be positive also. Correct. What else?
Yeah.
What? No, it can't give one. Think about it. Yeah, it can't give one for some reason. Okay, so yeah. Any other guesses? What is mod? What do you expect mod of a tilde ai square to be? This is actually Page's computation. But to do an actual calculation, you have to do this integral with the Haar measure and so on. But what do you expect it to be? What would you guess the answer is? Huh? Smaller than 1, clearly. But what value? What number should it be? Not 0. It can't be 0. It's mod square. Someone said the answer. What's the answer? Yeah. Good. So the answer is 1 over m. Why is the answer 1 over m? Because remember the sum of these eigenvalues has to be 1, right? So remember that sum of mod of ai tilde squared. Why? Because this is a density matrix. It has to trace to 1. It comes from the fact that the state is normalized. So this sum has to be 1. But all of these are for a generic state, the state doesn't like a1 1 tilde more than a2 2 tilde. So you expect all these values to be roughly the same. And what value do you expect them to be? Well, the sum runs over n terms. So you expect it to be 1 over m, exactly, right? So what do you expect this to be? So we expect that for a generic state, for generic state, or rather let me write the expectation of Sm. What does the expectation of Sm mean? It means you take Sm and you average over all states. Okay, then it will become an equation. Okay, so this is the expectation of Sm is equal to sum over I 1 over m log of m. Notice I had earlier log minus log of ai square, but the minus sign went away. I just got 1 over m. What's sum of I 1 over m log m? What is this sum? It's log of m. Because this is 1 over m, you summed it n times, so the answer is log of m. Right? That is, by the way, the Page result. Okay. The entropy in a generic state of a state of this kind is log of m. What was special about, what was the difference between m and n? M was smaller than n, right? So when we put this matrix A in this form, it was important that you could put it in the diagonal form this way, not in the diagonal form the other way. Okay. So the general Page result is for a generic state, the entropy is the expectation of the entropy. If you take a Hilbert space, then the expectation of the entropy is log of the minimum of m and n. If you drop the assumption that m is smaller than n, then this is the general assumption. This is the general result. Okay. Now, this is the result for the expectation value, and we cheated a little bit because what you gave me was the expectation value of ai squared. What we really wanted to compute was the expectation value of ai squared log of ai squared. Okay. So this answer has fluctuations, but the fluctuations of this answer, actually Page computed the first order fluctuations. He didn't do this full integral, but he expanded it out and he showed that the leading fluctuations were suppressed by m over n, okay, where n was this term. Okay. Now m over n, so the actual corrections to this, there are corrections to this result, and the corrections to this result are m divided by n. But m divided by m is a very small number. Remember, if you have 10 qubits and 20 qubits, then m divided by n is already 1 by 2 to the 10. Okay. If you have a very large system and you take 60% of it on one side and 40% of the qubits on the other side, then the m over n, the ratio of that is already a very tiny number. So this is a pretty good result. It holds to very high accuracy. This expectation value is also the entanglement entropy for almost all states except for very special states. This is the Page result. It's an important result in quantum information. You should all know it. Okay. So what is the result? You take a big Hilbert space, you divide into two parts. This size has e to the m, or this size has dim hm. This is hn, and the entropy is given by this. And remember, m and n are not the number of qubits. They are the dimension of the Hilbert space on the left and the right. Okay. You see this? Okay. This is the Page result. I have not derived it completely because I didn't do this integral with the Haar measure. Okay. If you open Page paper, Page also didn't do the full integral Haar measure, but you can see it's very plausible, right? We've kind of used a mean field approximation, but this answer is correct in the end, up to small corrections. I mean, there are no corrections in the expectation value of Sm, but the corrections tell you how much in the fluctuations of Sm. So fluctuations of Sm are different. The expectation value of Sm is correct. Okay, good. So, how did Page, so this is what I wanted to say about the Page curve. Are there questions about this? Yeah. No, we cheated a little bit more. We are computing the expectation of ai squared log of ai squared, and I used some mean field approximation where I replaced this expectation value and this expectation value inside the log. But that's okay if you have a lot of degrees of freedom. I had to compute the expectation of x log x. I instead computed the expectation of x and then the log of expectation of x. So instead of computing expectation of x log x, I computed expectation of x log of expectation of x. Okay, that's what I did. But it's fine when you have a lot of degrees of freedom. It's okay. Because, if when you have a lot of degrees of freedom, the distributions get very narrowly peaked. This is the central limit theorem. That's why often we are able to get away. When you look at a function of thermodynamic quantities, you look at a function of the pressure really has fluctuations. But you can still look at the expectation value of the pressure and look at the expectation value of a function of the pressure is the same as f of expectation value of the pressure. Because the fluctuations are very small in the thermodynamic limit. So this result is exact in the limit where number of degrees of freedom becomes very large. Okay, good. So now this result, as I want to say, is a correct result. There's nothing wrong with this result. This result is fine. Okay, it's obviously correct, and it's a result you can actually use in a system, in a quantum computer or something. Okay? However, the result was originally derived not to apply in condensed matter systems and other settings where it is still today used, but to apply to black holes. Okay, and how did Page apply the result to black holes? What Page said was, Page's argument was the following. Okay, think of a black hole. It starts off as a big black hole. Okay, so let's call this region black hole, this region outside. After some time, black hole becomes small. Outside is, outside now has much more matter. Okay? Then what Page said was, think of this as the following setup, where you have some total number of degrees of freedom. Yeah.
What is the order of magnitude?
Or this time, I'll say the order of magnitude of this time. It's roughly half the evaporation time of the black hole. Right now, there's no. I just said it became bigger to small. It's a cartoon, so there's no order of magnitude yet. There will be. Right now, I just said the black hole was big. Look, it became small. In this cartoon, there's nothing to say about time. This is just a cartoon, just to explain what the intuition was. Yeah. So the intuition page had was that you think of a box with a fixed total number of degrees of freedom. Okay. So this is the black hole and this is the outside radiation. Initially, you start with is that the black hole is occupying the full box. This is the initial state. And there's no radiation outside. Okay, the black hole is just formed. This is the intuition that page had. Okay. Intermediate. That the black hole is there and the outside radiation is there. Okay. And the final state is that everything, the black hole is gone and you have only the radiation. Black hole is gone, it's become very small, and almost all the box is taken up by the outside radiation. Okay, so this is an example of a black hole that's kind of big and then starts shrinking. Okay, and this cartoon is saying that you have a box, the box kind of describes all the degrees of freedom. First, all the effective degrees of freedom are in the black hole, then the black hole starts radiating, and then in the end, all the effective degrees of freedom are in the radiation. You can make this precise in many different ways. For instance, my colleagues at ICTS have recently set up a model where you have a spin chain. Initially, you have a lot of energy in one part of the spin chain, and slowly the energy leaks out into the rest of the spin chain. Okay, so that's kind of a model of this kind, where the energy is in one part and then it leaks out into the other part. Okay, if you believe this, and you believe this is an accurate picture of the black hole, and you said that the Hilbert space factorizes into HBH into the Hilbert space of the interior of the black hole, into the Hilbert space of the radiation, then you could use this to compute, you could use the page result to compute the expected von Neumann entropy of the radiation. Okay. And so this is sometimes called the page curve. At the beginning, the radiation has an effective Hilbert space which is effectively zero dimensional, okay, or one dimensional. It has no Hilbert space. So at the beginning, the radiation entropy is zero because there is no radiation to start with. Then it starts growing. In fact, this is also what Hawking would predict. At some point, remember, the answer for the page curve is you look at the log of the minimum of the dimension between M and N. Okay? So at some point, the size of the box flips so that the outside radiation has more degrees of freedom than the black hole. Then the entropy tracks the degrees of freedom in the black hole. Initially, it's tracking the degrees of freedom in the radiation. At later times, it starts tracking the degrees of freedom in the black hole. Okay. So the page result was this, that you expect the entropy of the radiation to go this way. This point is called the page time, and it's roughly half the evaporation time of the black hole. In fact, to be precise, it's not exactly half the evaporation time. You can compute what it is, but it's roughly on the black hole is half the area of what it was. Okay, so it's when the entropy of the black hole is reduced by half. Yeah. At the end, because the black hole has become very small. In the beginning, there are no degrees of freedom outside. So the black hole has all the degrees of freedom. So the entropy of the radiation is zero because there's no entropy to count. There's no Hilbert space. There's only, or maybe a very small Hilbert space. So the entropy of the radiation is very small. Slowly the radiation starts getting emitted. Once it starts getting emitted, it goes up. Okay. And because there are more degrees of freedom in the radiation. At some point, the number of degrees of freedom in the radiation become larger than the number of degrees of freedom in the black hole. However, at that point, remember the page argument tells you that entropy of a subsystem is given by the log of the minimum of the dimension of the system and its complement. So at that point, when the number of degrees of freedom in the radiation become larger in the black hole, the entropy doesn't keep increasing, rather it starts dropping. Okay. So sometimes this curve is drawn this way, and this is said to be the Hawking prediction. This is said to be the Hawking curve, and this is said to be the Page curve. See? So these two curves coincide for the first part of black hole evaporation, but stop coinciding for the second part of black hole evaporation. Okay. This is the argument that leads to the Page curve, and this is the intuition. Yeah, yeah. Is what? In the spin chain, you would get a specific page time that depended on the details of the spin chain. In the case of the black hole, the page time is roughly is of the same order of magnitude as the evaporation time of the black hole. In 4 dimensions, also scales with the cube of the mass. And it's not exactly half, but it's some numerical factor times half. The reason it's not half is because the radiation rate increases when the black hole is hotter. So this curve is not exactly up and down. It kind of does something slightly more complicated. Okay. It's not exactly straight up and straight down. Yeah. Called what? Called what? Sorry. Called what? Landau eraser. Oh no. That's not relevant here. That's why is that relevant here? There's no heat here. This is a statement of entanglement entropy. There's no dissipation happening here. There's no erasure or dissipation happening here. It's just a question of what is the entanglement entropy you expect for the radiation. No. You didn't lose any information here. The information here, you didn't lose any information here. The whole system is in a pure state, and the picture that you have is you start with this. No information is being lost here, and you have a barrier that moves across. So no information was lost here. Initially, this entropy is 0 because there was no radiation. The fact that the final entropy is 0 tells you the radiation's final state is pure. So it tells you all the information has come out. So this is assuming that there's unitary evolution, no information is being lost. And there's no erasure here. Yeah.
This argument will work fine for a relative state because it's gamma and all that. But lattice might contain some sort of structure here that how do you know that?
But I'm just about to say there's a more serious problem Page argument applied to black holes, but we'll come to that. Black holes might contain, but this is a very robust argument if you really had the factorization, okay, which we don't have for black holes. If you really have factorization, this argument just works on statistical principles. It's really like the argument we had of pure states and mixed states. It's almost kinematic. So you don't need much information about dynamics or anything that went in here. It's just kinematics. Dimensions of Hilbert spaces for most spaces give you this entanglement entropy. Yeah, but typicality is very general. Almost all states are typical states. If you look at the Haar measure, almost all the volume of the Hilbert space except for exponentially small parts are occupied by typical states. So you can compute how many states have an entropy which is within order epsilon here. That would be almost all states. Okay, so it's very robust. You don't need like special assumptions about the Hamiltonian. Doesn't matter. I mean, you might have you could discuss some very special initial states, but that we're not assuming that. You'd say you look at a generic black hole. Page will just say you just look at some other black hole. Why do you want? Maybe it's some very special states it doesn't work, but those are exponentially atypical, so we don't care about them. It's not highly interacting, doesn't make a difference, but exponentially atypical states might matter. Yeah.
I think the paper before is it straight or is it?
No, it's not. It's not actually that straight. You can compute its shape, because the radiation sometimes is slow in the beginning and fast later, but that's an unimportant detail. The fact that it's straight or not. It's not exactly straight. You can go compute what the actual path is by just looking at the entropy. Okay. Yeah. No, the outside, the entire outside. The radiation, whatever radiation was emitted. Huh? No. Everything outside the black hole. Why only the boundary? Yeah. The exterior of the black hole. You have the black hole and the exterior. That's outside. No, the radiation is all outside. Why do you have to consider? The Hawking curve keeps going up. The Page curve turns around at some point. Because the answer is given by log of minimum. At some point, which system is smaller changes. Okay. When the entropy of the radiation equals the entropy of the black hole, at that point they diverge. Yeah. Entropy of the radiation are the same. No, and yeah, and the entropy of the black hole and the entropy of the radiation. That's when, yeah. Okay, good. However, okay, so this curve is this this argument is correct, and this argument is a very robust argument if you had factorization of the Hilbert space. Okay? However, let me point out some that we spent a lot of time, we spent all the previous lecture trying to argue that the Hilbert space doesn't factorize into the inside of the black hole and the outside of the black hole. Okay. So if you really keep track of the full entropy of the outside of the black hole, that entropy we would say is always knows about the fact that the interior is pure. So the full entropy of the outside of the black hole, if you looked at the entropy of the outside, the region outside, S of R bar, we would say it would not track the page curve. Rather, that entropy would always know that the state is pure. Okay, so the next point I want to make is that the argument of page also involves factorization. And we just argued all this time that factorization for black holes is not a good thing to assume. In fact, if you were to argue that the degrees of freedom outside already keep track of the degrees of freedom inside, then you would be led to a different argument. Then you would be led to the argument that if you were to measure the entropy of the region outside, if you just measure the entropy of the region outside, means you look at the algebra outside all the way out to infinity and you measure that entropy just doesn't change with time, because it doesn't care about whether the black hole is evaporating or not evaporating. More precisely, maybe I should make a more precise statement. If you look at the entropy of this algebra on Scribe plus, and you look at the entropy of the algebra from minus infinity to a point u, then the entropy of this algebra, which I can call A of u, the page curve would have said that this entropy starts at 0, and you could, it kind of increases, and decreases. This would be the page curve. I should draw it in a different color. Well, let me draw it here. Sorry. So let me allow myself to make observations on a part of null infinity from minus infinity to u. Yeah. If I look at all observations here and I define the entropy of that algebra, you can define entropies of algebra just like you define entropies of Hilbert spaces. Then the page argument would suggest this. Okay. But this argument of holography of information would suggest a different curve. It would suggest the entropy is just always 0. We didn't keep track of massive particles. So it would suggest that this is not the entropy. It would in fact suggest that the entropy is just flat. If you keep track of all degrees of freedom outside, you don't lose information and then gain information. What is the page argument telling you? It's telling you in the beginning you don't have information about the full black hole. You have only limited information. Then the radiation starts emerging and you start getting more and more information. After about half the black hole has evaporated, then you start seeing the state is pure. And when you start seeing the state is pure, then the page curve goes down. This argument that we've been making tells you at the beginning, if you keep track of all degrees of freedom outside, you already know that the entropy is pure. You already know the state is pure. Okay? So it's a different answer from the answer that Page had. We would say that the Page argument as applied to black holes involves the same assumption of factorization as the Hawking's argument when it's applied to realistic black holes. Okay. I'm going to stop here, and because I want to say one more thing about how recent computations of the page curve, of which a lot have been done, I want to explain how those computations work. So those computations are not wrong. Okay, those computations are right, and I want to explain how those computations are performed. But I first want to explain that the page curve, the original argument of Page, is not applicable to black holes for the same reason that the original argument of Hawking is not applicable to black holes. Both the argument of Page and the argument of Hawking involve an effective factorization of the Hilbert space. Yeah, there's nothing wrong with Page's calculation. It is true if the Hilbert space were to factorize, it's a very robust answer. So you can work it, you look at qubit systems or, any other condensed matter system where things do factorize, and this argument is completely correct. However, if you keep track of all degrees of freedom, then, the argument we've been giving would suggest that the entropy is just flat. It doesn't care about the fact that you measured more. It just gives you this. Okay, there are some subtleties with this that I'm going to come to later. But first, is the zeroth order argument correct? See? What I'm going to explain next is how computations of the Page curve have been done in the recent literature, and whether there might be some way in which this argument applies to realistic black holes, but we'll discuss that. But first is the zeroth order argument here. Okay, so I made 2 points. First, I said, if you take a factorized system, then the Page argument tells you this. Okay, this is actually a bullet point, so we should write it somewhere. I'm now out of boards for writing the bullet points. So hopefully all of you have now seen these enough times. So I'll erase this. Well, maybe I won't. Let's see. Sorry. Maybe this can be kept till the end. And smooth horizon. Sorry, I won't erase it because I want to keep it till the end maybe. Symmetry of the smooth horizon. Okay, maybe I'll convert this into another summary point. Okay, so I'm continuing my bullet points here, and I'll now work only on those boards. And this is my, I don't know which bullet point, 7th bullet point. Okay, this is the Page argument, and this argument actually we just had earlier. So we should just say this we already know. Okay, so in this lecture so far I've made 2 bullet points. One of them is that if you assume the Page argument and you have a factorized system, then the entropy of one part of the system is given by the log of the minimum of the dimension of the system and its complement. And however, for realistic black holes, the entropy does not, the Hilbert space doesn't factorize, as we spent a lot of time discussing. So you don't expect the Page argument to really apply to a realistic black hole. If you were to measure the entropy outside, the claim would be you would always know the state is pure. You don't lose information. It's not like you lose information and gain information. Now, there was something else I had written here, which you might have worried about. Remember, I said that effectively, the Hilbert space might factorize if you coarse grain. So you could have asked me, okay, let me coarse grain a bit. If I coarse grain the degrees of freedom, then maybe the Hilbert space does factorize into inside and outside. However, the fact that the Page curve comes down is a very fine-grained effect. This entropy is not the coarse-grained entropy of the black hole. It's not the thermodynamic entropy. It is the fine-grained von Neumann entropy. It keeps track of very delicate correlations in different observations that you make outside. So, in the same regime where the Page curve is applicable, you're not allowed to just coarse grain. Okay? So, the Page curve is not a coarse-grained curve. This is not a coarse-grained curve. Because you're not allowed to coarse grain, your assumption of factorization is also suspect, because remember I said that locality and factorization works when you coarse grain, but the Page curve is not in the regime where you're coarse graining. Okay? That's why, even though the Page argument is a very interesting argument and an important argument that you should all know about, and you should go back home and try and derive it, it's not clear that it's applicable to realistic black holes. Okay, are there any questions about this part? Yeah.
Page curve was applicable.
Yeah.
What would that mean? That there was information?
No, it would not mean there's information loss. It would mean something rather strange. It would say that, the information is first not available, but later comes out in some way. However, the point is, if the Page curve was to work for a realistic black hole, then it would tell you that there is some assumption that you can make a factorization of the Hilbert space. Okay? And then, even though the Hilbert space is factorizing, it looks like you're losing part of the Hilbert space. So even though Hawking's principle of ignorance, which also assumed factorization, is somehow correct, it is still somehow the case there is some other error in Hawking's argument. Okay. So the key point of Hawking's argument really was to say there's factorization, the state outside is independent of the state inside. Therefore, because the state inside is going to vanish by causality, you look at the causal structure, and the state inside cannot communicate with the state outside. Therefore, no information from inside can leak outside. So you should trace over the inside. Okay. So the Hawking argument assumed only that factorization and locality. So if the page curve were to be correct for realistic black holes, then it would somehow have to be the case that locality holds effectively in some sense, but yet the Hawking argument is wrong. Okay. That's not impossible. It could be there's some regime in which the Hawking argument is wrong, but locality is correct enough for the page curve. But no one has ever found such a regime yet. The way the page curve calculations in the literature are done is in a different setting, which I'm now about to explain. Okay. Oh, I see. Okay, good. So, a fine grain entropy is an entropy which is of the kind we've been computing, right? This is the fine grain entropy. A minus trace of rho log rho. This is what we call the von Neumann entropy, which we computed. This kind of entropy keeps track, of what rho is, and what is this entropy if rho corresponds to a pure state? 0. And what is this entropy if rho corresponds to a mixed state? It's the thermodynamic entropy. Okay. However, a pure state, also has the same thermodynamic entropy. When we say we have the entropy of this room, we don't really care if the room is in a pure state or a mixed state. What we really say is we are making some coarse grain measurements, and then we ask what are all the microstates that are consistent with those coarse grain measurements. We don't keep track of all the degrees of freedom. So the thermodynamic entropy is different from the fine grain von Neumann entropy. The fine grain von Neumann entropy is an entropy where you keep track of everything. So when you derive this page entropy, we are looking always at a fine grain entropy. Remember the way we derived it, which I erased? We derived it by looking at this formula. So we have to keep track of all degrees of freedom, including exponentially small degrees of freedom. Why exponentially small degrees of freedom? Because remember I said that pure and mixed states are only different at exponential order, at e to the minus s order. So if you don't keep track of e to the minus s corrections, then you will never get this entropy going down or being 0. The fact that the entropy is 0 in the end is the statement that the radiation is pure. But that doesn't change the fact that the radiation also looks thermal to very good accuracy. Only if you keep track of very fine grained corrections will you see the radiation is pure. But if you're going to keep track of very fine grained corrections, then the assumption of factorization is also suspect. Okay? That's why there's a problem in applying the page argument to realistic black holes. Okay. Is this point clear? Okay, good. Now the last thing, I said I'd stop by 6. I'll stop very soon. Okay, so sorry for keeping you guys. Yeah. Okay. So I just want to now explain, just to get you up to, this was not the focus of these lectures, but there's been a lot of recent activity on actually deriving the page curve. Okay. I want to explain how those calculations which derive the page curve using the so-called island formula are carried out. So how are they carried out? When I said that, you don't expect black holes to follow the page curve, what is it that people are really doing? So what people are doing is something slightly different. The way those calculations are carried out is, you take a black hole in ADS. So let me draw, this is my black hole which has some matter, and then it forms and then it evaporates. Okay. Actually, this is not even exactly how, let me tell you exactly what people do. And then I'll say what people like to say. The way the calculations are done is, you take an eternal black hole in ADS. This is how almost all calculations are done. This is an ADS black hole. Are you familiar with the Penrose diagram of an ADS black hole? No? Some of you are, some of you are not. An ADS black hole is like the black holes we've been discussing in flat space, except ADS is like doing quantum gravity in a box. Okay. Many of the ideas I mentioned here about holography and so on have actually been made precise in anti-de Sitter space. It's a space that's not like the space we live in, because it's a space where the cosmological constant is negative rather than being positive as we expect it is in our world. But it's an excellent toy model for doing quantum gravity. So in this, it's like doing quantum gravity in a box. It's like there's a box at finite, and this is the boundary of ADS. Okay. What people do is they take a black hole in ADS, which is a gravitational black hole, and they couple it to a non-gravitational bath. This is a non-gravitational bath. The properties of non-gravitational bath is it doesn't have gravity. It's non-gravitational. That's how the property is. Okay. So it's a bath which does not have gravity. Okay. So, and then you take this black hole, and then what people do is you compute the entanglement entropy of, you make a division in the non-gravitational bath. So both sides are non-gravitational. I'm just drawing a curve here. And then you compute the entropy of a region R and the region R bar here. Okay. In the non-gravitational bath, it is true that the Hilbert space factorizes. Why is it true? Because that's a non-gravitational bath. It doesn't have gravity, as we just discussed. Okay. So in the non-gravitational bath, in fact, using the ADS CFT duality, we can write this entire system of an ADS black hole as a system which doesn't have gravity at all. Okay. And the way we write it is using ADS CFT. We would write it as a non-gravitational bath with a defect. Okay. So it's a non-gravitational bath, and at one end it has a defect. This defect is this was the time direction, and this was the space direction. What I have drawn here is only in space. I have not drawn the time direction on this diagram. Okay. So only space. If you draw the time direction, you should just extend this up in time. Okay. This was a Penrose diagram that was written in space-time. And here I've just drawn a spatial slice of this. And what I've said is, using ADS CFT, you can convert this entire system of a black hole with a non-gravitational bath into a non-gravitational bath coupled to a defect. Okay. Defect just means that the non-gravitational bath has a boundary. The boundary of the non-gravitational bath is the same as the boundary of this anti-de Sitter space here. Yeah, so in the gravitational picture, you have a gravitational ADS which has a boundary. And then this boundary is coupled to a non-gravitational bath. Using the ADS CFT duality, you can encapsulate the entire gravitational dynamics into the dynamics of this boundary here. Therefore, using the ADS CFT duality, this entire picture of gravity coupled to a non-gravitational bath can be converted to a non-gravitational bath with some boundary degrees of freedom, which is what defect means. Defect just means boundary degrees of freedom. Okay. If you take this defect is boundary degrees of freedom, if you take the matter to be of the right kind, then this entire system is sometimes described as what's called a BCFT. I'm sorry, I'm going to I have to apologize. I'm going to now just throw some terms at you. Okay. You can, just to make you familiar with some of the terms, I'm trying to explain the important physics, but I'm not explaining all the details. A BCFT means a CFT with a boundary. So what did I say? I said, take a black hole in anti-de Sitter space. Okay. Not a black hole in flat space. Take a black hole in anti-de Sitter space. Couple anti-de Sitter space to a bath. Using the ADS CFT duality, all the dynamics in the anti-de Sitter space can be captured into dynamics on the boundary of anti-de Sitter space. This defect is living at the boundary of anti-de Sitter space, and it's coupled to a non-gravitational bath. So the entire system can be dualized to a system where you have a defect coupled to a non-gravitational bath. There's no gravity anywhere in sight. Okay? In this system, you can now make a division and ask for R and R bar and compute the entropy of R with R bar. Okay. So Let me write what the physics is or the main points is. ADS black holes coupled to a non-gravitational path is described by a non-gravitational system with a defect, and defect just means boundary degrees of freedom, with a boundary defect. Okay, this is the thing you need to understand. Without, and I'm not explaining the details of this, but an ADS black hole coupled to a NG means non-gravitational path can be described by a non-gravitational system with a boundary defect. That's what I just said. Okay, in this non-gravitational system, which is just a non-gravitational system, you can divide the Hilbert space into two parts. And then you can compute the page curve of this part with this part. Okay. This is the page curve that's computed using the so-called island formula, which is a refinement of the Ryu-Takenagi formula that's used for computing entanglement entropy. So we can compute the page curve of part of a bath. And these calculations are fine, right? Exactly. Yeah. And these calculations are correct and they're nice. In fact, they involve this new technical development, which is this island formula, which was used to understand how these calculations work. And you can also understand these calculations as being performed on certain kinds of brains called Karch-Randall brains. So these calculations are perfectly correct. There's nothing wrong with these calculations. But there are calculations in this setup where we take an ADS system and couple it to a non-gravitational path. This adding this so this is the first point I want. This point is just true. Okay, you make these calculations. Maybe this is bullet point 9. And in this setting you can compute the page curve. Okay. Okay, I don't have time to explain how you compute the page curve, but it's done by some refinement of the Ryu-Takenagi formula, which is called the island formula. And the key part, let me just explain what the island is. The key part is when you compute these entanglement, entropies, there's an associated notion of what's called an entanglement wedge. The entanglement wedge is very much like that. Sometimes it might happen that degrees of freedom in one region describe degrees of freedom in another region. So it turns out that degrees of freedom in this region, which is called the radiation region, which is some part of the non-gravitational path, turn out to describe degrees of freedom in the interior of the black hole, which is called the island. Okay. So the statement is that the entanglement wedge of the radiation region turns out to describe degrees of freedom in the interior, which is called the island. Okay. I haven't explained what entanglement wedge is, but really it's like that kind of a formula. If the degrees of freedom here describe degrees of freedom here. Okay. Okay. So this calculation is completely correct. There's nothing wrong with this calculation. Okay. Okay. Are there any questions about this part? I know I've been very quick and kind of schematic. I now want to explain one place where there's some disagreement in the literature, and I want to explain what the two pictures are, and then I'll stop. Okay. How to do that calculation? How to do that calculation? Are you asking how you compute the page curve?
No.
You see, you have a state, so you can compute the entanglement entropy of this part with this part. So that's a detailed calculation that involves a refinement of the Ryu-Takenagi formula called the island formula, which I don't have time to go into right now. Otherwise, your badminton tournament won't happen. So let me not go into that. But you can do the calculation. Yeah. If some of you want, you can come to me later. I'll explain to you how these island calculations are done. Yeah. The point is you can do the calculation. Okay. Is this point clear? Okay. So this is the 9th bullet point. Now I want to make one last point. However, and there's some disagreement on this in the literature, the picture that emerges if you apply this to realistic black holes is somewhat different from the picture I've been proposing. And the picture that emerges if you apply this to realistic black holes is the following. Let me erase this. Is the following, okay? No, the island is really the entanglement wedge of the radiation region. It's the fact that when you compute the entropy of the radiation region, the way you're supposed to compute the entropy is you're supposed to extremize area of the island by 4g plus the entropy of this radiation region union the island. Okay, where this is a so-called this formula. Well, okay, I don't want to go into too many details, but let me just say quickly. I don't know how many of you are familiar with the Ryu-Takenagi formula. The way the Ryu-Takenagi formula is done is you try to compute the an area of a minimal surface in the bulk or an extremal surface in the bulk that's anchored to a certain region on the boundary. You can add one loop corrections to the Ryu-Takenagi formula. And what that tells you is you compute not just the area, but the area by 4g, you extremize the area by 4g plus the QFT entropy of that region. The island emerges because it turns out when you compute area by 4g, usually islands are very expensive to create because there's a 1 over 4g term here. It turns out the island emerges, and you will find a lot of discussion of this, because when you compute the, this QFT entropy of this radiation region and this island, that can sometimes compete with this A over 4g term. So when you extremize this, you will find that this Ryu-Takenagi surface, in fact, is not anchored to the boundary, but it's just kind of sitting in the middle. And that's the island. That's the Ryu-Takenagi surface. Okay, so that's how the island emerges. Okay. That's a detail of how the page curve computation is done. What I want to explain to you guys is what's the picture that would emerge from the island computation, and what's the picture that I've been trying to discuss in the rest of the lecture. Okay. So using this, you of course do get the page curve in this case of a non-gravitational bar. Okay. Okay. What's the picture that emerges from this? And this is the last point I want to make. So the picture, bullet point 10, okay, 10, fine. Okay. So the picture that emerges from this is the following. Okay, now bullet point is not really a bullet point. It's something that maybe some of you guys can clear up. Okay, the picture that emerges is, think of this evaporating black hole. Yeah. So the people who like the island proposal and think of it as a good model for realistic black holes will say the following. They'll say, think of this black hole that's evaporating. And think of some region which is outside the black hole. Like some region like this. And let's call the region which is very far from the horizon. Okay, so maybe it's some region very far from the black hole. And think of this region, call this region R bar, and call this region R. They would say you should use the island formula to compute the entropy of you. In this region, gravity is very weak because you're far from the black hole. So you should use the island formula to compute the entropy of this region R bar. When you do that, you will find that the degrees of freedom in this region R bar describe degrees of freedom in an island in the black hole interior. Okay. I'm marking this island by I. Okay. So the island formula suggests that degrees of freedom in I, of freedom in R bar, are redundant with degrees of freedom in I. Where I is in the black hole interior. Okay. So this is what the island rule suggests. If you were to apply it to a real evaporating black hole in flat space, in asymptotically flat space. The calculations, as I said, are done with a non-gravitational bar. But this is what the island rule would suggest. Okay. I don't actually agree with this picture. At least some of us do not agree with this picture. And we would say that the degrees of freedom in R bar are not only redundant with, if you have a case where you have a real black hole, Okay, and what I'm about to say, you should realize is it issue where there's disagreement in the literature. Everything I said so far, I think there's not much disagreement in the literature. In what I'm about to say now, there is. We would say that the degrees of freedom in R bar, even though gravity is weak, so that's why I'll write this in blue. Okay, we would say that weak. I hope there's one blue marker, and I'm about to stop. We would say that weak gravity is not the same as no gravity. So we would say that these calculations were done in the case where there was literally no gravity in the bath. And as a result, these page curves were derived. We would say weak gravity is not the same as no gravity. And the degrees of freedom in R bar are redundant not only with degrees of freedom in the island, but with degrees of freedom everywhere, including all the way here. So in some sense, we would say that the island is not just restricted to inside the black hole, but it extends all the way out till the boundary of the radiation region. The question of whether there is this blue region or not is a question of some disagreement in the literature. Okay? So we would say the alternative is are redundant with all degrees of freedom. So we would say there's no island, not because there's something wrong with the fact that these degrees of freedom describe degrees of freedom in the interior, but we would say these degrees of freedom also describe these degrees of freedom, these blue degrees of freedom. It's not like these degrees of freedom do not describe these degrees of freedom. You know what the picture I've been saying there is that if you have a bounded region and you look at its complement, all degrees of freedom in the complement are described by degrees of freedom in the bounded region. All degrees of freedom in the bounded region are described by degrees of freedom in the complement. Okay? So we would say not only the island is actually bigger. The island, in fact, in a theory where you really have full gravity and not a non-gravitational bath, the island extends all the way out. The island doesn't stop here. It kind of grows. Okay? With all degrees of freedom. Okay. This is something that, there's some and if this is the case, then you would get that flat page curve that I discussed for a realistic black hole. Okay? If this blue statement is correct, then you would get the flat page curve that I discussed. So point number 10 continued is that for a realistic black hole, you can get two answers. You can get either the page curve or you can get this flat curve. And the difference between these two answers is, does the island stay confined to the inside of the black hole, or does it kind of grow and go out till the radiation region? Okay? That's the difference. Okay, so these are the alternatives. And this is a function of time. Okay? And the reason there's some disagreement is, people say, maybe there's some way of dividing the degrees of freedom here, by doing some effective coarse graining so that you can get an island. Okay, no one has ever specified what coarse graining you exactly need to do to get an island in the case of a realistic black hole. Okay. But, if you take that picture seriously, or you think that the non-gravitational bath is the same as the region far away from a black hole, then you would get this picture where there's an island. Okay. However, what we would say is the fact that there is an island is telling you that you should be careful of the unusual properties of gravity. The fact that there's an island, even though you're very far away, is telling you that degrees of freedom here describe degrees of freedom here. So these unusual properties of gravity, the degrees of freedom in one region might be redundant with degrees of freedom in the other place, are already visible to you here. So it is natural that in fact you should take this property of holography of information seriously, and you should think that degrees of freedom here also describe degrees of freedom here. Okay, now there's some papers in the literature and there's some disagreement, but this is something that maybe some of you can clear up. Yeah. Okay, so are there questions? Yeah. There are no review papers in this. There are papers making slightly different claims, but which you can look at. For instance, there's this paper that we wrote on the inconsistency of islands, and then there are papers by Folstad and others trying to argue that islands are okay. But if you look at this paper on the inconsistency of islands and you look at the list of references, you'll find some papers that argue that that paper is wrong. But it's actually an interesting topic, and it probably will also teach us something about gravity. Okay. Okay. So I'm going to stop here, and I'm going to summarize my 10 bullet points, and then you can all go for badminton. So we've had a long, we've had many hours of lectures. I hope some of it has gone through. If not, it's sometimes useful to hear these words. Maybe the next time you hear these words, they'll make more sense. Let me just remind you, we just started with the classical geometry of the black hole, the derivation of Hawking radiation, the simple version of the information paradox. We discussed how pure states are very close to mixed states, and that resolves these simple versions of the information paradox. So at least next time you find some popular science presenter or even some popularizer of science saying Hawking computed Hawking radiation, which was thermal, therefore there was a paradox, you should say, jump up and say, that's wrong, that's not a paradox, because pure states are very close to thermal states. So that by itself is not a paradox. And in fact, that's not what Hawking actually said. In Hawking's paper, Hawking actually invoked the principle of ignorance and said you should trace over the interior, and he invoked locality. And by using that, he argued for a more refined paradox than one based just on his computation. However, we should realize that gravity has unusual ways of localizing information. And this is a very important property of gravity. So I said at the beginning that the reason we study the information paradox is to learn new things about gravity, not because the information paradox is empirically important. One of the things we learned, which was very interesting, is that, in a theory of gravity, if you look at operators in a bounded region, you can represent them in the complement of the bounded region. And we proved a version of this result by looking at the algebra on null infinity, and where we proved that if you looked at the algebra on all of Scribe plus, you could approximate every operator of this algebra, that's what A means, in terms of operators near the past boundary. That's the realization of this cartoon. Then we've also discussed the page argument for black holes. So this resolves, that refined version of the information paradox. Then we discussed also the page argument. This is an argument which is generally an argument that's important to know in quantum statistical mechanics, which tells you about the entropy of a subsystem in a factorized Hilbert space. Then we said, look, the page argument might or might not apply. It looks like there's a problem in applying the page argument to realistic black holes, because in a realistic black hole, as we argued there, the Hilbert space doesn't factorize. Then the last part, which have been somewhat schematic, I said that, the page curve has been computed in the recent literature. And the way the precise computations are done is by taking an ADS black hole and by coupling the ADS black hole to a non-gravitational bath. In the non-gravitational bath, the Hilbert space does factorize. Why? Because everything I was saying about the lack of factorization was a statement about gravity. In the non-gravitational bath, the Hilbert space does factorize. And then, using very clever techniques, people have computed the entropy of part of the bath. And they have found that this entropy follows the page curve. There is, disagreement in the literature about whether the entropy that follows the page curve is the entropy that you should compute in the case of a real black hole. Okay? So advocates of the page curve would like to say you take a real black hole, you make a division, and you go very far from the black hole, and that's like a non-gravitational bath. And then the radiation entropy follows a page curve and it describes an island. However, some of us would say that the fact that you're seeing an island is telling you that these effects of gravity are still important. And, the radiation region not only describes the island, but the full entropy, the full degrees of freedom inside. And if you do that, then you would find that the entropy of the outside doesn't follow a page curve, but it remains flat. Okay. So maybe some of you can help to clear up this issue of which picture is more accurate for realistic black holes. So as you can see, this is still an area of active and interesting research. So thank you for your attention. I'm sure all of you are tired. I'll stop this.